In this section, we start looking at triple integrals in different coordinate systems. So this gets a little deep, and I left more of the slides in this video than I usually do because it's sometimes hard to see these things. So we've got cylindrical coordinates, and then we've got spherical coordinates. Cylindrical coordinates are basically the three-dimensional version of polar curves. Spherical coordinates are sort of a world on their own. So we'll see how deep we want to go into this. I left more pictures than usual in here because sometimes it's a little bit harder to see these things, and I want you to see them and I want to give a little explanation of what they look like. You'll find additional pictures of what these objects look like in spherical and cylindrical coordinates in the PowerPoint. Sometimes it's just easier to write these things in cylindrical and spherical coordinates, and sometimes it's the only way to write these things. So the objects that you're working with are going to be a little bit different than your normal ellipsoid and paraboloid. So in cylindrical coordinates, we add a third dimension to polar coordinates. So instead of having just an r and a theta, you've got an r, a theta, and a z, which gives you your height. If you look at this picture that's up here, there's actually more of this picture than we need for my description. So this set of r, thetas, and z's includes r's between 1 and 3 and z's that are greater than 0. So you're going to have a little hole here and then a circle on the outside. And so you're going to include that piece there, but only from this plane up, right? Not that piece down the bottom. What do you have? You have a cylindrical shell that has a hole that has a radius of 1. That's what you get in cylindrical coordinates when you look at something like this, S of r theta z's, where the z's are positive and the radii are between 1 and 3. The theta is not given, so to create that whole circle, we would go from 0 to 2 pi. All right, here's another illustration of what cylindrical coordinates look like. You've got a point in space that has a radius, a theta, and a z value, right? How far is it up along the z-axis? Down the bottom, you'll see where that theta comes from. That theta is the angle that it makes with the positive x-axis. So here's the positive x-axis. Here's the angle that it makes with the positive x-axis. So that means that we can break those x's and y's into r cosine thetas and r sine thetas, just like we did in polar coordinates. What does that make the radius? That makes the radius square root of x squared plus y squared, or we could square both sides, and we'll get r squared equals x squared plus y squared, no different than before, equation of a circle. A little something about notation. Remember when we did triple integrals, we had the insidemost integral in terms of functions of two variables. So your top and your bottom surfaces are going to be h of xy and g of xy, and then your g of theta and h of theta are the boundaries of that polar defined region in the xy plane, and then you've got two angles, alpha and beta, that tell you how far to go. So if you only wanted part of that cylinder with a hole of 1, then you would only go part way around, maybe 0 to pi or 0 to pi over 2, and they would give you different shapes depending on how far around that circle on the base you wanted to go. All right, here's what it looks like. And then there's a second half to this too. So if I want to integrate with respect to volume, right, f of r theta z with respect to volume over some region, right, the triple integral over d, right, some region in space d, with cylindrical coordinates looks like this. Now, if you look at the region in the base, you can start separating these. Instead of integrating over the volume, you can pull the z out and now integrate that over the area. When you do, your limits of integration become functions of x and y. Well, if there are r's and thetas, how do those things become r's and thetas? This is how those things become r's and thetas. You replace the x and the y with r cosine theta and r sine theta. So now what you have is a formula for something in cylindrical coordinates where you've got an f of r cosine theta that used to be your x, r sine theta used to be your y, dz, and then don't forget there is still that r there when you're evaluating in polar form, r dr d theta. So now that we're in cylindrical coordinates, we're going to be integrating dz r dr d theta. So we're going to have 4 things to put after that function. It's going to be the function dz r dr d theta, because the first thing we're going to do is integrate with respect to z, then we're going to integrate with respect to r, then we're going to integrate with respect to theta. So those are theta boundaries, those are r boundaries, those are z boundaries. Okay, How does this all work? Here's how it works. Suppose I've got this shape here. That's a terrible looking integral, isn't it? I want to integrate, if I had this in xy terms, xyz terms, the y's would go from 0 to 3. The x's would go from negative square root of 9 minus y squared to the positive, and the z's would go from 0 to that top piece over there, right? That would be the side of that cone that's over here. The cone stops here at y equals 0, so you notice that the y's, that's the outermost limit of integration, starts at 0, so it only starts at here and goes up to 3. Right? So as you want to find that volume, you'll go from 0 to 3. What can I do to turn this into cylindrical coordinates? Well, first of all, what are the dz limits? The dz limits are the ones that are closest on the inside. So those dz limits, I can go back to the idea that x squared plus y squared equals r squared, and replace that x squared plus y squared with an r squared. And now the square root of r squared is just r. So my z limits go from 0 to 9 minus 3r. Right, how about the r limits? If I want to find a radius in this xy plane, you notice that the x's actually go from negative 3 to 3. Okay, if you come all the way in the back here, right, that's negative 3, that's positive 3. But what is the radius? The radius goes from the center to a point on the outside. That radius goes from 0 to a max of 3. Doesn't matter whether the radius is going this way as it sweeps around, comes over to the other side, your radius will be out here. It'll still be going from 0 to 3. When the radius is all the way along the y-axis, it'll still be going from 0 to 3. So your r values go from 0 to 3. And then your theta values. Where does theta go? Well, you only want half the circle, so half the circle goes from 0 to pi, right? Why? Because it's a half circle. If I wanted the whole circle on the base, I'd go from 0 to pi, but I only want half the circle. 0 to 2 pi, but I only want half the circle, so I'm going to 0 to pi. All right, how do we set this up? We need a triple integral of, we'll call it 1 dz r dr d theta, right? Where the z values go from 0 to 9 minus 3r, the r values go from 0 to 3, and the theta values go from 0 to pi. So let's do the inside one first, and I end up with just a 9 minus 3r, right? If I'm integrating with respect to z, I'll get a 9 minus 3r. Now that 9 minus 3r gets multiplied by that r. So my second integral becomes the integral from 0 to 3 of 9r minus 3r squared. This time integrated with respect to r. So I'll get 9r squared over 2 minus, if I do 3r to the third over 3, you notice the 3's cancel, so it'll just be minus r cubed. Evaluate at 3, evaluate at 0. Right, when I do that, 3 squared is 9, so 9 times 9 is 81. That gives me 81 over 2 minus 3 to the third is 27. Right, common denominator, 54 over 2. And so 81 minus 54 gives me 27 over 2. Now my last step is just to do the outsidemost integral. So the outsidemost integral will give me the integral from 0 to pi of 27 halves d theta, which really just gives me 27 pi over 2. All right, so in this case, it looks much easier to do it in cylindrical coordinates than to try to deal with all those limits of integration in terms of radicals. Okay, if you go back to the original question, that's what the original question looked like in terms of radicals. All right, let's look at another problem. This problem asks about the mass of a solid paraboloid, and I will give you the little formula at the end. We'll do a lot more with masses and centers of masses and stuff in the next section. So find the mass of that solid paraboloid. I tell you what the limits are for the z's. I tell you what the limits are for the r's. And then for the thetas, you want it to go from 0 to 2 pi. It's an upside-down paraboloid. If you look at that density function, rho of, that's rho. That funny-looking p is a rho. Rho of r theta z is 1 plus z over 9. So it looks like the higher up you go, the more dense the object becomes. And it doesn't matter what the angle measure of the radius is. That's not part of the density function. So what you're going to do is you're going to set up a triple integral, and it goes like this. Rho dz r dr d theta. So you got rho dz r dr d theta. That's how you're going to set up that triple integral with the limits of integration that I gave you before. All right, so let's set this up. This can be sort of a pain to solve because I think we're going to end up with some funky substitutions, but at least let's set this up and see where this goes. It becomes a triple integral. We said the rho goes on the inside, so our rho was 1 plus z over 9 dz, don't forget the r, dr d theta. And my limits of integration, I've got a 0 to 9 minus r squared. That was the first limit of integration. That's with respect to z. With respect to r, we said it went from 0 to 3, and then the thetas go from 0 to 2 pi. So the first time I integrate this with respect to z, and then evaluate it at that r, do you see then I'll end up with a function of r that I can use in the next step. Okay, let's see what I get. I'll end up with a z plus z squared over 18, because I've got a 9 there, and when I multiply it by 2, I get 18. Evaluated at 9 minus r squared and 0. So this is going to give me 9 minus r squared plus 9 minus r squared squared over 18. Right, when I put a 0 in, I just get 0 plus 0. So the funky thing is now I'm going to have to expand that whole first piece. Or the whole second piece, rather. Let's come over on the side and do it over here. All right, so this gives me 9 minus r squared. And then let's write plus 1/18 times. 9 squared is 81 minus 18r squared plus r to the 4th, right? First term squared, 2 times the insides, last term squared. That's how I expand a binomial. All right, so I get 9 minus r squared. If I take 81 and divide it by 18, I will end up with, if I could divide by 9 halves. So plus 9 halves minus r squared plus r to the 4th over 18. That's just the first one. Now don't forget that I've got to multiply this by r before I integrate with respect to r. So 9 plus 9 halves is going to be 27 halves. Okay, so let's simplify this as much as we can. So 27 halves times r. The minus r squared and the minus r squared will give me a minus 2r squared. Multiplied by that r will give me a minus 2r to the 3rd. And then the last term, when I multiply it by an r, will give me plus r to the 5th over 18. Great. What do I do with that? Now I integrate this from 0 to 3, because those are my r limits of integration. Right, so I haven't integrated anything yet. All I've done is multiplied that by r. Now integrate with respect to r. So when I do that, I'll get 27r squared over 4, right? 2 times 2 gives me 4, minus 2r to the 4th over 4, plus r to the 6th over 18 times 6, evaluated at 3 and at 0. Not to spoil the fun, but I evaluated this already and I got 27. All right, then the last step is easy. Evaluate from 0 to 2 pi, 27 d theta, and that'll end up giving me 27 times 2 pi, 54 pi. All right, so that's how I do it in that's the mass in cylindrical coordinates. All right, let's take one more look at cylindrical coordinates, and then I'll do a separate video for spherical coordinates. All right, let's take a look at this volume. Volume of the solid bounded by that plane and the paraboloid. So the plane is on the top. The plane puts a lid on top of my paraboloid, and then the rest of it fits in underneath. I'm going to do a triple integral. I'm going to set the function as 1. That's how I set up the volume. How do I turn this into something in spherical coordinates? Cylindrical coordinates. First of all, I can replace this x squared plus y squared. X squared plus y squared is r squared. So that's how I can replace it. If I want to know where the z values go, the z values go from this object here up to that lid at 25. So it goes up to the lid at 25, and it starts on whatever that object is there. So that object is x squared plus y squared, which we're actually calling r squared. So the z values don't go all the way down to the xy plane. The z values start at r squared, and they end at 25, right? That's the highest z value that you're going to get, because that plane puts a lid on my solid. All right, how about the radius? Well, the radius goes from 0 to 5, right? If I set x squared plus y squared equal to 25, I'm going to end up with r squared equals 25, r equals 5. So the r values go from 0 to 5. And then I need a complete turnaround, so the thetas go from 0 to 2 pi. All right, so when I set this up, this is not bad at all. I'll end up with a triple integral of 1 dz r dr d theta, where we said the z's went from r squared to 25, the r's went from 0 to 5, and the thetas went from 0 to 2 pi. Right, so this inside piece over here is simply going to give me 25 minus r squared. Right, so I'll get 25 minus r squared, r, don't forget that r dr, integrated from 0 to 5. Multiply out that r first before you integrate. You'll get 25r minus r to the third, and now actually perform the integration. So you get 25 r squared over 2 minus r to the fourth over 4, 5 and at 0. So you'll get 25, 5 squared is 25, minus 25 to the fourth over 4. All right, set up your common denominators and add, and this will give you 625 over 4. And then the last step is just to integrate from 0 to 2 pi. All right, so if you integrate that from 0 to 2 pi, maybe you can see what's coming. Integrate from 0 to 2 pi of 625 over 4 with respect to theta, and all you get is 625 times 2 pi over 4. 625 pi over 2. Okay, that's the volume. And that's the end of cylindrical coordinates. I'll do a separate video with spherical coordinates.